Oh, yes. So I don't know why this has removed Ritakshi, but maybe she will be joining soon. Okay. So meanwhile, let us discuss this idea of Brilliant zones, which we were discussing. So the slide which is appearing on your screen is the one showing the Brilliant zones for various three-dimensional lattices. And we have already discussed how we can draw the three-dimensional or any dimensional Brilliant zones. So these are nothing but the Wigner seed cells drawn in the respective or drawn for the respective lattice. And I hope you all know what is a Wigner seed cell. Well, so just if it is Vitakshi or so. Okay, anyway, fine. So now let us move further to see a very interesting relevance and application of the X-ray diffraction, where the idea of these reciprocal lattice is very, very useful. You have studied X-ray diffraction in your lower classes, and I'm sure you somewhere would have done this, that what is the Bragg's condition for diffraction of X-rays from a crystal, and that turns out to be n lambda equals 2d sine theta, correct? And the basics are very simple, that you have some atomic planes in a crystal. So these horizontal lines are representing atomic planes. Just a minute. Is Ritakshi able to join us? Ritakshi? I don't know if she was actually removed or what. Is Ritakshi present in the class? Okay, you all please mark your attendance meanwhile. And if someone can contact Ritakshi, then that will be nice, so that if she is facing some problem to join the meeting or what. I am not able to see her request after the recording was started. Or maybe later on we can share the video with her, because I don't know why this was done by Google itself. Fine, let us proceed further. So the basic idea here is that, okay, we have, I mean, what is the idea behind X-ray diffraction is that you have atomic planes in a crystal. So those are parallelly arranged because of periodicity condition. So you may have some specific plane, suppose set of planes with some interplanar spacing being d. Then if you shine X-rays to such an set of atomic planes, what will happen? There will be constructive interference under certain circumstances at specific angles, say theta, where you will be finding constructive interference among the X-rays coming from various planes, getting reflected from various planes. And that is what leads to the maxima in the X-ray intensity at certain angles, and that is called the X-ray diffraction. And this was very important result which was obtained by Bragg. So basically, to see Bragg's diffraction, what are the necessary conditions? That the wavelength lambda must be smaller than the interplanar spacing, or at least of the order of interplanar spacing, and that is why X-ray is a suitable choice for observing the X-ray diffraction pattern. Since in crystalline materials, the typical interatomic spacing is of the order of bond distance, or say lattice constant, just a rough order of magnitude. And then you may see that, okay, visible spectrum falls in this order, so it's something like 300 to 700 nanometer. So if you shine visible light to a crystal, there won't be anything like X-ray diffraction, because the wavelength is too large for visible light to produce diffraction pattern. And since the X-rays do have their wavelength in the region of or of the order of interatomic spacing of the order of angstroms, that is why they are very good, perfect, suitable choice for studying the X-ray diffraction. I mean the diffraction pattern from the crystals. And here is a set of typical lattice constants for certain crystals, so you can get the idea that why visible spectrum is not a suitable choice. And another very important and interesting thing here is that in a crystal, it's not like, I mean, when we do derivation of this law in our lower classes, we see that, okay, only two planes, we show the X-rays coming from two planes, put the condition for X-ray diffraction, and then obtain this condition. But in practice, it's not just two planes, but there is a large number of planes which actually takes part while X-rays are being scattered from a crystal. So typically, each plane reflects something like 10⁻³ to 10⁻⁵%, 10⁻⁵ times the intensity of the incident X-ray incident on the crystal. So typically, to represent the full beam, to reflect the full beam, we require something like 10⁻³ to 10⁻⁵ atomic planes to deflect the whole beam and to see something really visible in the diffraction pattern. So that is a set of planes, or that is such a large number of planes which do take place in X-ray diffraction. So X-ray diffraction can give you information as deep as of the order of 10⁻³ to 10⁻⁵ number of planes. Although that is not very large when we compare this to the X-ray, I mean to compare this to the bulk crystal, because 10⁵ planes are not too big for a bulk crystal. They are very few. You would say something like only lying near the surface. Now, there is one very interesting question. So this is showing a very typical example of X-ray diffraction pattern. I have taken this graph from Kittel, so you may refer to Kittel for details. So this is showing X-ray diffraction pattern for powdered silicon. Powdered silicon means you have small crystals of silicon. It's not a single crystal. I hope we had a talk in some of the earlier presentation regarding polycrystalline and single crystalline materials. So powder crystalline means you just take a single crystal, crush into the form of some sort of powder. That is what we can call the powdered crystalline or polycrystalline samples. And then something like sodium chloride, which you use in your homes, house salt. So this there we have a powder, right? Salt is in the form of powder. So each grain in that salt can be seen as small crystallite of sodium chloride. But then that each grain has a very large number of atomic planes in it. If you go to the lattice constant of sodium chloride, then you may realize that, okay, for forming a crystallite of say 1 millimeter, how many planes must be there? So they are very large, definitely going to be very large in comparison to 10 raised to the power 3 or 10 to the power 5. You can do that small exercise yourself. Now, this graph has something really interesting, that, okay, you are finding that at certain specific angles, you are having a maxima in the peak of the X-ray being observed when they are scattered from a crystal or powdered sample of a silicon. And then we name these peaks. Okay, there is 110 peak, 220, and so on. Then, of course, if somebody asks you why we observe the peaks at specific angle, you should refer to the Bragg's law, because it is satisfied. It is at specific angles or specific values of 2 theta or theta, you would say, that you are observing maximum in the intensity of the X-rays. Now, okay, fine. Now there is one question here, that why do we have different intensity for different peaks? So as per this expression, there is nothing or no mention about what should be the value of the intensity. So this means this expression is not really complete. This expression is incomplete. It can't describe the complete X-ray diffraction pattern of any crystal. It can tell, okay, at what angle the peak is going to be observed, but it cannot tell that what will be the intensity of the peak. So where is the gap missing, or what is missing here? So fine, this I think I already conveyed you. As per Bragg's law, for a given wavelength, say copper K alpha, suppose this is the X-ray being generated from a copper source out of K alpha transitions, the wavelength comes out to be of the order of 1.54 angstrom. The peak position you can find out then at a specific angle. So what does this sentence mean? That okay, if you know what is the wavelength, you can find out at what angle peak is going to be observed, given that you have some specific interatomic spacing. So if you know, suppose sodium chloride has a FCC structure, then you can find out what will be the interplanar spacing for say 110 plane or 100 plane, and then from the lattice constant you can find that, and then accordingly you can calculate at what angle the peak should appear. So that is fine, but then this expression nowhere talks about the intensity that I already conveyed. Now let us proceed further towards how we can calculate intensity actually, and what is the more general description of X-ray diffraction caused by a crystalline substance. So basically what we need to find out is the scattered wave amplitude. What is the amplitude of the scattered wave? Once we know the amplitude of the scattered wave, you can find out the intensity from amplitude star amplitude, right? If you know amplitude of any wave, you can find out A star A will give you the intensity. So our first objective is to find out the amplitude of the scattered wave. So for doing that, we will begin with the fact that crystal actually is invariant under any translation of the kind given in this expression. So this we have already done in very detail. So I won't be doing this again. So what is the important fact here is that any translation of this kind, where A1, A2, A3 are the permittive vectors of a particular lattice about which we are talking, and U1, U2, U3 are some integers. So any translation defined by this translation vector is invariant, or the crystal is actually invariant under such translation. If so, then electronic density in a crystal will also be periodic according to the same rule, because atoms are arranged in a periodic fashion, so will be the electrons, and hence we can say that electron density does also follow this kind of periodicity, right? What does it mean? That electron density must be periodic according to this rule, right? Isn't it? So if you have electron density some specific value at R, then you take any T, electron density at nr plus T is also going to be exactly the same. I hope there should not be any doubt in this. This is quite straightforward. Now let us focus on simple one-dimensional case to keep our life simple rather than directly jumping to three-dimensional case. So all this content has been taken from Kittel. So I refer you to the solid state physics by Kittel to go through the details if you need it. Fine, so let us stick to one-dimensional case. This we already have done, that okay, electron density is to be periodic. So in that case, how we can write down the electron density? Electron density can be written with the help of a Fourier series. This also we have done in very detail. So that is how we can write down such a periodic electron density with the help of Fourier series. This also is straightforward. So I am again skipping this. I mean, doing this in very brief. Now, since the periodicity can be written with the help of the Fourier series, now we can also write down this. We can verify actually. Okay, what if periodicity is? What is the periodicity? If we say, because here we are using A, right? The periodicity. But we can verify also that if you substitute x with x plus a, what you will be finding is, you just simplify this expression, you will be finding finally that n of x plus a is equal to n of x. Means Fourier series is very comfortable and capable of producing that periodicity of electron density. So this means it is a correct way of representing a periodic electron density. Means n of x plus a is n of x. Similarly, in general, we can find out n of x plus t is equal to n of x if we take a three-dimensional Fourier series. Let's not move to 3D as such. So there is another way of writing this Fourier series that is called exponential form of Fourier series. That also you have done somewhere, I'm sure. So I'm not going into detail of this. So here, if we use this form, then n of x can be written as this summation where np is the Fourier coefficient corresponding to a specific term. So p now here can be any integer, positive, negative, or even 0. P is a set of all the integers as per this. So here, what was the constraint in sinusoidal or cosinusoidal case? P was a positive integer. And for both the cases. So if we merge the two terms, so here we have done nothing but used those Euler identities, and then you can do that yourself or refer to the how we can get this exponential form of the Fourier series. So then we will finally find out that okay, this is how we can write. This is equivalent way of writing electron density. Well, and another thing which is given in Kittle itself. Again, I am leaving it to you as some small homework. The electron density must be a real function, right? Because it is a physically measurable quantity, so it cannot be a complex thing, right? It cannot be a complex number. So it has to be a real function. It has to be a real quantity. Therefore, for this thing to be satisfied, these Fourier coefficients have to satisfy certain constraint, and that constraint comes out to be very simple. That if you take complex conjugate of Fourier coefficient corresponding to minus p, that should come out to be equal to the Fourier coefficient at p. Means n star minus p should be n of p. This is also a straightforward derivation given in Kittle. I leave it to you, assuming you are senior and mature students and have done it or can do it yourself. In case you will face this difficulty, you can then contact me, no problem. Fine. If we put this constraint, we can write down, okay, the value for Fourier coefficient will come out to be equal to 1 by a in one-dimensional case. You know how to find out Fourier coefficients. So this will be 1 by periodicity, isn't it? Times 0 to a. So this is how you can obtain these Fourier coefficients. Well, now, when we have done it for 1D case, we can straightforward expand our formalism for three-dimensional case. Means in case we are dealing with actual crystals, which are practically three-dimensional periodic structures, the electron density can be written to be in this form. Now, there is one-to-one correspondence between these two. This part up to here was done to realize, okay, how we can use reciprocal lattice to represent a physical quantity. Now, this is where our reciprocal lattice starts relating to the physical quantities. So electron density is a physical quantity, right? Then most of the time students have a question that, okay, where is this reciprocal lattice, which seems to be a completely mathematical concept? Does it relate to the physical reality? So here is the physical reality, that it is helpful in representing the periodic electron density. So in 1D, this can be done this way. In 3D, we can write the electron density by using this same. This is also Fourier series. And these are our respective Fourier coefficients. And these are that G. I hope you remember that G vector was periodicity in reciprocal space. Just like we have T as the periodicity or translational invariance in real space, we have G vector as a periodicity in the reciprocal space. So this is the same thing, NP e raised to the power iota. So this 2 pi by a 2 pi p by a can be seen as g vector in 1D case. I hope we had done that, right? So similarly, in 3D case, this is g vector in 3D case. So how we can obtain Fourier coefficients back from that? So using the same thing, we can obtain Fourier coefficients in case of three-dimensional crystal, where 1 upon V is the volume of the unit cell. So here it is a length. In 1D, it has to be 1 over length. In 2D, it has to be 1 over area. So because here A was the length of the unit cell in 1D case. In 2D, it will be 1 over area of the unit cell in 2D case. In 3D, it has to be volume, 1 over volume. Fine. I hope it is clear. So now, what will be our reciprocal lattice vectors? Now, this is where those reciprocal lattice vectors or the transformations from real to reciprocal space are important. So how to obtain G vector? G vector can be obtained from those B1, B2, B3 vectors, which follows from your real space vectors according to these relations. Okay, so now everything is there with us. So once we have real space lattice, so we have its primitive vector. So what is the algorithm is? You have been given a particular crystal structure. Try to identify its corresponding lattice, and then find out the Bravais lattice vectors or primitive vectors for that Bravais lattice. From that, you construct the reciprocal lattice using this formulation or this transformation. Then you find out G's, the reciprocal lattice vectors, according to this, where V1, V2, V3 are the integers. And then you can write down the electron density in terms of the reciprocal lattice vectors. So means something in real space can be written equally well with the help of something in the reciprocal space. So that is something useful mathematically at least. And you can verify that if we use this representation and use that T vector, I hope you know what is that T vector, U1, A1, U2, A2, U3, A3, then you can verify that n of R plus T actually will come out to be equal to n of R. You can try that as an exercise. So this is R plus T substituted here. R in place of R, we are writing R plus T. So there will be two terms here. Now we substitute the values of G from here and T from the expression on previous slide. And then if we multiply them, and I hope you remember what does the dot product of real and reciprocal space lattice vector give us. So AI dot BJ vector gives you 2 pi delta IJ, right? So using that whole expression, we will be able to find out that, okay, this part will give you nothing but 1 because these are integers multiplied with each other. So e raised to the power 2 pi iota times an integer will give you 1. So this, with the help of this, you will finally be able to prove that n of R plus T is equal to n of R. Okay, let me check if I'm still online and everything is going smooth. Okay, is everything going fine, or is there any question till now? Any question till now? Okay, fine, sir. Could Ritakshi join us? Is Ritakshi present? I think yes, because there are total 31 participants. Ritakshi, are you there in the class? No response. I don't know. Maybe she is not able to join us. Okay, fine. Anyway, we'll share the video of the class. Now, if it is clear till now, let us move further and try to move to our actual target, which was to obtain the amplitude of the scattered wave, right? So now let us refer to this figure here and assume that we have a crystal. This is our crystal specimen, suppose this shaded area, which is containing many atomic planes arranged in the crystal. And assume that we are incidenting the X-ray beams like this. So this is the wave vector of the X-ray beam, K vector. And this is the width of the beam, suppose, because of course we are going to take a beam of a finite width. And this beam is interacting. Okay, I'm sorry, there was some technical problem and I was ejected out of the meeting. Let me again come back to the topic. Okay, I need to share my screen. Okay, so here is the screen. I hope it is visible now. Is it visible? Okay, it is coming shortly, maybe.
Yes, sir.
Okay, now screen is visible. Fine. Now I hope you could hear I don't know. I don't know where I left. I was offline. So this part was clear that, okay, if you use this representation for electron density, then we can verify that indeed electron density comes out to be periodic with periodicity defined by T vector, translation vector. Is this part clear? Was this okay? No, I don't know. Okay, some people are saying okay, fine. Now let us come to the scattered wave amplitude. Fine, I got your response. Fine. Now this is what we want to discuss now. Let's suppose we have a crystal specimen. Here is the X-ray beam being incident. So X-ray beam now is represented with the help of K vector. K vector is the wave vector for the incident X-rays. So the direction of K vector is nothing but the direction of the incident beam. I'm sure you all know this. And the incident beam now is written with the help of a plane wave. Suppose it is something like a plane wave, because X-rays will be having, they are nothing but electromagnetic waves, and those are nothing but the electric and magnetic fields varying sinusoidally. So we can represent them with the help of e raised to the power iota k dot r. I'm sure you all are very comfortable with this. So now suppose let us take, we took small volume element in the crystal, which is dV, and first try to find out the scattered wave amplitude, which is getting scattered out of this small volume of the crystal specimen, dV. So that actually the scattered wave amplitude is given by this expression. Now you will ask, why this expression? Well, this is so because how much X-rays will be scattered depends upon the electron density present at particular point, because electromagnetic waves are the waves which are scattered by the charge density in a particular region, because electric field in the electromagnetic wave interacts with the charge, and then charge oscillate and then produces secondary electromagnetic waves, which are nothing but the scattered electromagnetic waves, right? So it is directly proportional to the electron density at a particular point, obviously. Similarly, it also is proportional to dV, the volume. Bigger is the volume, more will be the scattered wave amplitude. As simple as that. I mean, bigger is the volume in which X-rays and electron density interact. Higher is going to be the intensity, right? Similarly, it is it is not just the two factors over which it is proportional. It also is proportional to the phase factor. I mean, if the phase difference, that is where that constructive and destructive interference came into picture, right? So it is that phase factor which also has to be taken care. So this is where the phase factor is sitting. So if the phase difference, so this is talking about that phase difference, k minus k dash vector. So this is your k vector. This is your k dash vector. So total change in angle between incident and scattered beam is k minus k dash. It is given by this, right? Dot r. So suppose this is your r vector. So now I will be talking to you about this part in detail, how this came, how we arrived at this, um, rather than directly jumping to what is the result. But okay, this is something which we need to pay attention to. But okay, given this phase angle and phase factor, we can obtain the scattering wave or scattered wave amplitude by using this expression. Then we can write down this with the this k vector minus k dash vector is delta k, the total change in the wave vector, correct? Dot r. So now the question is how this follows. Let us try to pay attention to this figure. Okay, I've not done it in detail. So you will need a little intuition, or a notebook will be very helpful. So you try to do as I am I am telling you now. So what is the total phase angle? First, we will realize that total phase angle is like, okay, what is the phase difference, total phase difference between this incident and this scattered beam is what we want to first find out. And for this, let us first try to assume that, okay, this angle is phi, which is the angle between the perpendicular drawn on the incident beam and the point joining. This is suppose the full beam size of the X-ray. So this is actually r vector is the vector joining the point on crystal where one portion or one end of the beam is falling, and the second portion where second end of the beam is falling. Fine. So this r vector is uh, giving that displacement, right, from O to maybe O dash is this r vector. Okay, and this phi is the angle between r vector and this perpendicular to the k vector. So this is perpendicular to the k vector, incident wave vector. Now, if this is so, then if we extend this line, I hope you can follow the cursor. So this line, if we extend, and if we extend this line, right, and if we refer to this triangle, actually, what will this angle be? This is 90 degree. So this angle, if this is O, let us write down this is O dash. This angle will be nothing but 90 degree minus phi, because this is phi, this is 90 degree. Sum of all three angles of triangle is 180 degree. So this angle will come out to be equal to nothing but 90 degree minus phi. So will be the angle between k vector and r vector. I hope you can realize from here what is the angle between k vector and r vector. That is going to be 90 degree minus phi, because if I increase this, this angle is 90 minus phi. So the angle between r and k vector will be opposite to this, isn't it? Opposite angles. So that is also going to be 90 degree minus phi. Could you visualize this? Maybe I should have put some what you call more arrows here in the slide, but I didn't realize that because I was just uh, aware that, okay, maybe this will be done. So is it clear? I mean, could you see this? Could you visualize what will be the angle between r vector and k vector? This is going to be 90° minus phi. Is it clear? Is this clear?
Yes, sir.
Okay, very good. So, okay, if this is the angle between k vector and what you call r vector, then what will be the phase difference uh, for this case? Okay, let us first start with the simple identity that if we have a path difference of lambda, which is equal to the wavelength of the incident beam, then what will be the phase difference for a path difference of lambda? That is going to be 2 pi, right? For path difference of lambda, phase difference is 2 pi. What will be the path difference for, what will be the phase difference for path difference of x? So here, what we want to find out is that, okay, what is the path difference between this beam reaching here and this beam reaching here? So this basically path difference tells you that, okay, what extra portion of path has to be traveled by this end of the X-ray beam to reach to the surface of the crystal. So that is the additional path difference which will be traveled. So what will be the path difference? This path difference will be given by this triangle, or you can find out if this is, say, base of the triangle, this is perpendicular, then this is phi. So what will be the path difference? Can you do a little small trigonometric calculation in your notebook and let me know what will be the path difference for this portion from here to here? What will be the path difference? Yes, you can type your answer, or
R sin theta.
this will be
R sin theta.
r sine theta. Correct. This will be r sine theta. So now let us find out what is the phase difference between this point and this point. Phase difference between this point and this point, or you can see the phase difference between this point and this point, right? Why so? Because up to this point, the all waves in X-ray beam are at equal phase, because this is a wave front perpendicular to the beam, right? So the phase here is exactly same as the phase here, and the phase difference between this point and this point is same as the phase difference between this point and this point, right? So X-ray gets an additional phase difference while reaching here. And what is that phase difference? So that is where we have to apply that identity now. For a path difference of lambda, phase difference is 2 pi. And for a path difference of 1 unit, the phase difference is 2 pi by lambda. Correct? And for a path difference of r sine theta, sorry, it is phi here, it is not theta, it is phi, right? So for a path difference of r sine phi, what is going to be the phase difference? 2 pi by lambda times r sine phi. Is this clear?
Yes,
Is
sir.
this clear? Anyone having any doubt? Those with doubt, please type your question. I will be happy to help you. Clear, fine. Well, so this is giving you the phase difference between this point and this point. But total phase difference, now if you see the output beam, this is your output beam, right? This outgoing beam, you could say. So total phase difference actually has to come from this path difference and this path difference as well. There are two additional paths which are traveled by the beam of the X-rays while going out of the crystal. So total phase difference. So how we will be getting this path difference? Again, we can assume this is some angle. Now what we have here is k dash, not k. Correct? So this path difference will come out to be, okay. Before I move to that, okay. What was the path difference? This was, for this portion, this was 2 pi r sine phi by lambda. Correct? And what is this 2 pi by lambda? 2 pi by lambda was nothing but k vector. So that is why we can write down the the phase difference for this part is k vector dot r vector. We can write it that way also, right? That the phase difference for this part is nothing but k vector dot r vector. Similarly, for this portion, we will be in a position to say that the phase difference will be nothing but k dash vector dot r vector, right? Rather, it will come out to be equal to minus k dash vector dot r vector. That you can verify yourself. So the phase different to this part is this one, correct? K dash vector dot r vector. So can you get it done yourself, or is it clear, or I need to say something more about this? Is it clear?
Sir, where does the sine phi part go?
Dot product. It goes in the dot product.
But sir, shouldn't it be cross product if there is sine?
No. What is the angle between r vector and k vector? It is 90 degree minus phi. It is not phi. Phi is not the direct angle between k vector and r vector.
Okay, sir, got it.
Right? So that's what is the thing here. Fine. So that goes in the dot product. So if this is clear, then fine. So this is what is the total phase angle. K vector. Now this is a vector equation defining the full phase angle. So k vector minus k dash vector dot r vector. So this gives you total phase angle. So that total phase factor will be e raised to the power iota. So now you know, if you have been given the phase difference, then what will be the total phase factor appearing for the amplitude equation? That will be this one. So again, I hope you have done it somewhere in your wave optics or something like this. So I'm using it directly. So that is what is going to give you the scattering wave amplitude. The scattering wave amplitude is given by this equation. So where this is your delta k dot r vector. So delta k now is nothing but total change in the wave vector. So this is another way of looking at this. So delta k vector can be written to be like this. Now in the form of a vector diagram, you can say. So if this is your incident wave vector, this is your scattered wave vector, k dash vector. So delta k is giving you the total change in the wave vector because of scattering process faced by X-rays while interacting with the crystal. Fine. And this is where something important also comes into picture. One thing is called elastic scattering, and second is called inelastic scattering. In the inelastic scattering, what happens? The momentum,
K prime equal to K.
Yeah, the
K prime equal
magnitude,
to K.
the magnitude doesn't change. There is no loss of energy, right? In case of elastic scattering, the magnitude of wave vector doesn't change, means wavelength doesn't change. And the only change in k is in the form of the angle. So usually when X-rays do scatter, there is no change in momentum and wavelength remains same. So that is a elastic scattering. Fine. And then we only need to bother about angle. But in some cases, there may be change in momentum. For example, in neutron scattering, they may transfer some of their momentum to the atomic lattice. So that kind of scattering is called inelastic scatterings. Somebody has not muted the mic. Please mute if you don't have to ask something. Fine. So in inelastic scattering, we have to take care of that change in amplitude as well. So this is general formalism so far. Now what we are using is, okay, let us talk of stick to elastic scattering only, which is the situation for X-rays. So we can take that the magnitude of k dash vector is same as the magnitude of k vector. The only delta k is because of change in the angle, right? Because of scattering. Now the amplitude of the scattered wave coming from that small volume element dV is proportional to local electron. This I already told you. I mean that amplitude is proportional to local electron density, the volume element, and all. So this is the same thing written once again. Now here the electron density can also be written with the help of Fourier series, right? So what we are doing here is we are trying to replace that periodic electron density with the Fourier series. So if I do that, then this expression will turn to this expression now. Now here, along with integral, a summation came into picture, which is because of Fourier series. So scattered wave amplitude is summation over G, where G is the reciprocal lattice vector. So now that is where those reciprocal lattice vectors start appearing in the picture. So this is summation over G dV. So now this Ng is now the Fourier coefficient of the electron density. It is not electron density directly. So Nr and Ng, note the difference. This is electron density in the real space. This is the Fourier coefficient of electron density in the reciprocal space. E raised to the power. Now same thing. What we did is, I mean, we will be getting one term corresponding to e raised to the power iota g dot r. So that's what has come here, e raised to the power iota g dot r. And then there is another term appearing already here, e raised to the power minus iota delta k dot r. So that's the second term here. So this is the scattered wave amplitude, now written in terms of reciprocal lattice vectors. Is this clear? Or any question till now? Is this okay? Am I audible there? Is this clear? Okay, fine. Now you would realize one more thing, that this integral will be zero in most of the cases, except for the case when G is equal to delta K. Now you will be a little confused, or you may ask, why so? This is so because there is a huge oscillatory term. This is the oscillatory term of the integrand, right? And this is nothing but a sinusoidal function. So now more is the deviation of G. I mean, suppose when, take the first case when G is equal to delta K. In that case, this is zero. This term is zero. So this is one. This whole function is one. So integral is going to be non-zero, right? And some maximum value, whatever it is. Now, as G is some standard thing. Now G can't change, right? It is a fixed thing. It is fixed for a crystal. So where, now you may ask, okay, where is the structure information of crystal coming into picture? It is sitting in the G. And where is X-ray information coming into the picture? It is coming in delta K. So basically delta K is taking care of the experimental measurements, and G is taking care of the theoretical or the arrangement of the crystal part. So this is representing the X-ray part. This is representing the crystal part. So this delta K, if it is not equal to G, then there is a deviation, right? More is the deviation, higher is this value sitting in the power of the exponential, more is going to be the oscillations in the exponential function, right? E raised to the power, say for example, 0 is a constant function. E raised to the power 1 dot x, iota 1 into x will be a sinusoidal function having some periodicity. You can verify. E raised to the power 2 into iota 2 into x will be a sinusoidal function with double or a half time period, or half periodicity, not time period, but half the periodicity, and so on. So more is the oscillatory nature of this function, and sine function is a very beautiful function, right? Because if you take the integral of sine function over one period, what will that give you? Zero, correct? Positive, the area under positive half will cancel the area under the negative half. Now, but we are not taking the integral here over the periodicity, right? We are taking the integral over the volume element. But if you have a periodicity which is so small, suppose the periodicity in the volume, okay, if the volume element is of this size, say 10A, suppose A is the length of the say unit cell, right? So 10A. So what does it mean is that in the one set of dV volume, which is 10A bigger, you will have 10 sinusoidal waves. Out of those 10, or it may be something like, okay, not exactly 10, but 11 sinusoidal waves. Suppose there is some deviation, the volume is not necessarily integral multiple of the sinusoidal waves being generated because of this. So suppose they are 11 or maybe 10.5. So what will happen out of that? The as many as complete number of sinusoidal waves are lying in the volume, they will contribute zero to the crystal. They will contribute zero to the integral, because positive half of each complete wave will cancel the negative half of that complete wave appearing in the integrand. What you can find out maximum is the value equal to say half of the integral value, half of the, I mean, area under the cycle, area under the half cycle of that sinusoidal wave. I hope I'm able to convey it to you. You need to visualize it a little bit, because if I had a board in with me, then I could have drawn it on the board. So because of that, more is the deviation of G from delta K, higher is going to be the oscillatory nature of this function, and lesser will be the contribution of this term to the overall integral value. So that is why this integral will be non-zero only for the case when delta K is equal to G. Is this okay with you? I mean, are you fine with this part up to here? Or is there any question till now? Please let me know. Is this fine, or is there any question? Am I audible there? It is fine for Harish. What about others? Is it clear? Okay, very good. So now this condition actually is telling you where you will find out the maximum scattered wave amplitude. And what is the meaning of maximum scattered wave amplitude? Is maximum intensity. So this expression is another way of writing Bragg's diffraction condition. Means delta K, whenever delta K is equal to G, will tell you that there will be a maximum. So this is also another form of Bragg's diffraction condition. This is also known as Bragg's diffraction condition in the reciprocal space in form of reciprocal lattice vector, right? So G is your reciprocal lattice vector, delta K equal to G tells you the Bragg's condition in the reciprocal space. So having done this by today, tomorrow we will be discussing other aspects of it. So tomorrow I will be showing up that how this delta K equal to G can be used to obtain this 2D sine theta equals n lambda. So I leave it as a homework to you. You go to Kittle's book, try to obtain these, try to go through these. So now you should see that if all these are lying on screen like this, the way they are putting up in the book, you will not be in a position to understand the physical meaning of what is happening here, right? But then you go, try to read the text and try to see how he has arrived from here to here. And then I will be happy to see any answers, any questions from you regarding this. So with this, that's all for today. Then tomorrow we will be discussing other physical aspects of this Fourier interpretation of the X-ray diffraction. Fine, that's all for today. The time is already over, so I will be taking a break here. Any questions, if there are, I will be taking them tomorrow. Okay, have a nice day. Bye.